want to put together everything that we've just talked about into a strategy for graphing rational functions. And they do take a long time if you're graphing by hand, I'm not going to lie. I do recommend still using Desmos to help you check your work and things, but it is still a good skill set to know how to do this by hand. Even if you're not plotting points at the end, just to be able to look and find these key values, right? To be able to find where the asymptotes are, or where, if there's symmetry or not, and so on. So these are key skills that are really helpful in upper level mathematics. Again, even if you're using technology to graph, right? So let's go ahead and try a few examples together. So the first thing that's recommended that you do is that you test for symmetry. So this, we've already actually learned this, and this goes back to the idea of even and odd functions. So remember that if you have y-axis symmetry, that is an even function. So what happens is you plug in negative x, but get the original function back out, okay? So something like that x squared function, let me see if I can find the picture of it real quick. That was here, is an even function. It has symmetry with that y-axis. It's a perfect mirror image. So if you plug in x or negative x, it doesn't matter. You get that same function back out. The second one we talked about here was symmetry with the origin, and we call those odd functions. And what we do is we plug in negative x, and what happens is that all signs change in the original function. So basically, you get the opposite of the original function back out. And we actually had that here. So this is actually an odd function. You have this kind of symmetry with the origin, which is like a diagonal symmetry. And what happens is that when you plug in, let's say the positive version, you get, in this case, 1. But when I plug in -1, I get a -1 out. So all the signs end up switching here. And that is an odd function. So it just kind of helps to know if you have these mirror images happening. Other things you want to find are really key points here. So intercepts are key points. So the y-intercept, if there is one, you plug in 0 for x. And then for the x-intercepts, we solve the equation. You actually set the whole function equal to 0. But what happens is when you cross multiply, the denominator will cancel. So you're really just setting the numerator equal to 0 there. You want to find any vertical asymptotes, which involves looking at where the denominator is 0. And that's also good too, even if there's no asymptote, you may have a hole there that you need to address. You're going to find your horizontal asymptotes. And then if you need to, plot extra points. So it recommends plotting at least 1 point between and beyond each x-intercept and vertical asymptote, etc. So you want to just pick as many extra points as you need to in order to find the pattern of the graph, right? So that you're really confident that you know what's going on. So let's do a few of these examples. So the first thing we're going to look at is symmetry. And remember, to do this, we're going to plug in negative x instead. So when I plug in negative x, I have negative 2x minus 1 over negative x minus 1. I actually can simplify this a little bit more because I could factor a negative out of each part. And then I could cancel those negatives. So I end up with 2x plus 1 over x plus 1. So now I compare. Is this the original function? No, it's not, right? It's different. This has plus signs, this one has minus signs, so it's not the original function. So it's not even. And then I also check to see if all signs have switched. Now, 2 of the signs switched, right? Here, from negative to positive, but the other 2 did not switch. They still stayed positive in the end. So it is not the opposite either. We'll say the opposite. So it's not odd. So for symmetry here, at this point, I'm just going to write none worth noting. So it doesn't mean that there's not other kinds of symmetry, but for our purposes, if there is, it would be of a different kind. So for right now, no symmetry worth noting here. All right, so the next thing I'm gonna do is I'm gonna look at my intercepts. So for my y-intercept, you're going to plug in x equals 0. So I go back up to my function here. I end up with -1 over -1, which is 1. So I do have a y-intercept at 0, 1. Let's see, 0, 1. I'm just going to put that right on the graph for now. And then for my x-intercepts, remember that means that y equals 0. So technically what you're doing is you're setting the whole function equal to 0. But what happens is you end up cross multiplying here or trying to cancel the denominator. So when you multiply it by x minus 1, this ends up canceling out. So you can actually just solve the numerator is equal to 0. And that's what this notes up here. So I would add 1 to both sides. Divide by 2, and I get x equals 1/2. So I do have an x-intercept at 1/2, 0. So let's see, right there. All right. So I've done my symmetry. I've done my x and y intercepts. I'm now going to look at my asymptotes. So for your vertical asymptote, remember you're looking to see if the denominator is equal to 0. Or I guess I should say, I know I have not equal to, but where that denominator would be 0. You do want to make sure you're simplified first. This is simplified. I can't break it down any further or factor anything. So we are simplified. My denominator would be 0 here at 1 when I add 1 to both sides. So there is a vertical asymptote at x equals 1. And then for my horizontal asymptote, remember you have that table that you can look at. Let me go back to it. And in this case, I want you to notice that there's the same powers, right? They each have a power of 1 as their highest degree here. So when your powers are the same, then your horizontal asymptote is the ratio of the leading coefficients. So here, my powers are the same in the top and bottom. So my horizontal asymptote is at y equals, and then I take that ratio. So my top one is 2, and my bottom number here would be at 1. So at 2. Now, what I'm going to do is I'm going to, in another color, I'm going to use light yellow, because this is not actually part of the graph, but I am going to draw those asymptotes in just so I can kind of see it. So I have a vertical one at x equals 1, which is right here. And then I have a horizontal one at y equals 2, which is right here. Okay. So that just kind of reminded me that it looks like I'm going to end up having some sort of splitting going on with the graph. So I'm kind of like avoiding these two lines here for my rationals. Okay. Now I only have 2 points. So I don't really have enough information. I really need a few more points to graph. So I'm probably going to pick a couple more points over here and then some points in this area. And what your book recommends for this one is they recommend picking the following values. I'm going to write it horizontally just so I can fit it in. So they chose the values of -2, -1, they did 3/4, they did 2, and they did 4. And then they plugged these values into the function. And what they got was 5/3, 3/2, -2, 3, and then 7/3. So for this step here, remember you're plugging into the original function. So for instance, let me do 2, 3. I would choose x equals 2, and I would plug that in. So 2 times 2 minus 1 over 2 minus 1. That means 4 minus 1 over 1, which is 3 over 1, which is 3. So they took those values and they just plugged them into the function one at a time. There is no shortcut for that. You just have to kind of pick some values. So again, once you kind of see your intercepts, I would pick some over here to see what's going on. And then I would definitely pick some in this range too, so I know what's going on. So let me graph these. So -2, let's see, -2, 1, 2. Now 5/3 is the same thing as 1 2/3, so like 1.67. Let's see, 1, 2. So I'm not quite at 2, I'm maybe like right here. At -1, you're at 3/2, which is 1.5. So maybe right there. And then at 3/4, you're down here at -2, 1, 2, so about right there. So you can kind of see that pattern now, I think, well enough. And then on the other side at 2, you're at 3, 1, 2, 3. At 4, 1, let's see, 1, 2, 3, 4, you're at 7/3. So let me see, that would be 2 1/3. So here. Now, if that's not enough for you, you're going to keep going and find more points. And what you should get is a graph that looks like this. So it's going down this way. And then this side is going to follow the same pattern. I know I have a vertical asymptote and I know I have a horizontal asymptote. So that's a big help here. You need to keep that in mind, that this graph is going to go flat as it heads to the right, and it's going to shoot up as it heads towards 1 here. So using those asymptotes, that's a really big piece here to help you figure out the pattern. But again, if you need more points, so maybe choose a few more, maybe choose 6, and then maybe choose things closer to 1, maybe like 1.5 or 1 1/4, and get a couple more points there until you're really confident that you understand the pattern. All right, let's do another one. All right, so first thing I'm going to check here is my symmetry. So I plug in -x. And actually, guys, I'm going to change this. So I'm going to go fix it in your handout too. So if you notice that it's updated in your handout, then that's good. But this one is really similar to the last one. Let's do something different. I meant to type in this problem. So I'm going to do this one instead. And again, on your handout, it should be correct because now I'm noticing this. I'll go fix it on the handout. But let's do something different. This one's too similar to the last one. So we're going to mix it up a little bit here. Okay, so I'm still going to start with symmetry. I'm going to plug in my -x. So I have 3 times -x squared over -x squared minus 4. Now, because you're squaring, that negative is going to cancel. And you should notice pretty quickly that you have the original function back out. So we have an even function here, which means that we're going to see symmetry with the y-axis. So we should see some mirror imaging along the y-axis. So that's a nice tip to keep in mind. In our last example, we didn't have those two symmetries. Now you may be saying, well, there is some kind of symmetry, right? Because I do have that kind of diagonal image, but it's not at the origin. It's been shifted on the graph. So that's why it's not showing in our first step. All right, next we're going to look at our intercepts. So I'm going to do my y-intercept first. So I'm going to plug in x equals 0 there. And I have 3 times 0 squared minus 4. Now 3 times 0 squared is 0, and 3 times 0 is 0. Here I have -4, so my answer is just 0 here. So I do see that I have a intercept right at 0, 0, a y-intercept. Plot that in. Now I'm going to check my x-intercepts as well. So I'm looking at y equals 0 here. But remember, what's going to happen with that denominator when you go to solve with 0 is it's going to end up canceling itself out in the solving process. So you really only need to set the numerator equal to 0 here. That's a little shortcut, only for rationals. All right, so when I divide by 3, I still get x squared equals 0. And when I go to take my square root of both sides, I just get x equals 0 again. Don't forget it is plus or minus, but it doesn't matter with 0. So I do have the same x and y intercepts here. It is still good to check both though, just in case you have an x-intercept that was missed in the first computation, right? So you still want to do both processes here with rationals because they can be quite complicated for their graphs. Now we're going to check our asymptotes here. So I'm going to start with the vertical. I am going to notice that this is actually a simplified rational expression. So you do want to check that when you're doing your asymptotes. So this is simplified. So in that case, I'm just looking at the denominator equals 0. I would add 4 to both sides. And then when I take plus or minus that square root, I see that I get 2 vertical asymptotes, one at +2 and one at -2. For my horizontal, notice here that you have the same powers again on the top and the bottom. So your highest power is 2, your highest power is 2. I'm trying to find my little cheat sheet there. So if you need to go back to that little cheat sheet here, when the powers are the same, then the ratio of the leading coefficients is going to be your asymptote. So my asymptote is going to be y equals, I have 3, and then here is a 1. So let me draw those in for a second. So let's see, at 2, I have a vertical. At -2, I have a vertical. And again, these are not actually part of the graph. That's why I'm kind of doing them in the light yellow, just so for my own graphing purposes, I can kind of see where they are, but they're actually not on the graph. 1, 2, 3, and then I have a horizontal one running this way at 3. All right. Now I clearly do not have a lot of points. I only have 1 point. I need to plug in a lot more values here to figure out what on earth is going on. So what your book plugs in, they chose, let's see, -3, -1, 1, 3, and 4. And when they plugged those in, they got 27/5, which is the same thing as 5 2/5. They got -1, -1, another 27/5, which is 5 2/5. And then here they got 4. All right, so let's plug those points in. So let's see, we have -1, 1, oh, sorry, -1, -1, +1, -1. I have 4, 4, so 4, 1, 2, 3, 4. And then I'll do the harder one, so -3, 1, 2, 3, and then I have 5 and 2/5, so like a little bit over the 5 there. And then I also have +3, 1, 2, 3, and then 5 and 2/5. Now again, there's not a lot of detail here, so you may want to pick a few more points to plug in. And remember, you're just plugging right into the original problem. So let's say I chose the number 1 here, right? So we're just picking some values. We plug them in. 1 squared is 1, so 3 times 1 is 3. 1 squared is 1, 1 minus 4 is -3, and then we get that output of -1. So that's all they're doing. They're just picking points and plugging in. If I'm being honest, I would probably pick more points here. This doesn't seem like enough information to me unless you're really familiar with these kinds of graphs. What ends up happening is your graph looks like this. So you end up getting a graph that looks like this. And again, like I said, I would maybe pick a few more values to plug in if you're not familiar with these graphs. Notice I do have that symmetry with the y-axis. So I do have this nice perfect fold down the middle. I do still have my asymptotes. So I'm going this way, right? We're going towards positive infinity as we come in towards those values of 2 and -2 on the x-axis. And here I'm going towards negative infinity down this way. And then I do have that horizontal asymptote running here. I will note that there are rare cases where a line does cross over a horizontal asymptote, like usually on 1/2, not always both, but most of the time you don't see that. So usually your asymptotes are not typically crossed over, although there are some exceptions there. So I did use that to help me draw. And again, I would definitely use Desmos here to check. So you can always use Desmos to plug in your answer here to check that as well. All right, and let's try one more. All right, let me make sure I copied this one correctly. I did, okay. And we're gonna use that same process again. So I'm gonna start with my symmetry. So I find negative x. Now, because you have 4 negatives, they are all going to cancel. Negatives cancel in pairs, and same thing on the square. So you do have the same or original function. So this is even, which means it is symmetric with the y-axis again. So we do have the same sort of symmetry here. I'm going to look for those key points, those intercepts. So my y-intercept is when I plug in x equals 0. So I would have, let's see, 0 to the 4th over 0 squared plus 1. Well, that's just 0 over 1, which is 0. So I get that same kind of intercept again here of 0, 0. Still check your x-intercepts, make sure we haven't missed anything. Now, x-intercepts are when y equals 0, but like I've said before, what's going to happen when you set this equal to 0 is that denominator will end up canceling, because you'll either cross multiply or you'll cancel out your fractions. So that denominator will cancel. So you really only set the numerator equal to 0 here. And the only time anything to the 4th power is 0 is if the x value is 0 itself. So you don't have anything new here for your answer. If you did want to solve though, you would actually take the 4th root of both sides, and you do take plus or minus if you have even roots. So the 4th root of 0 is still 0, and we don't need the plus or minus. So nothing too helpful just yet. Next, I check for asymptotes. So I start with vertical first. Make sure that this is simplified before you go into anything with asymptotes. Remember, if it's not simplified, then your denominator will just be a whole instead of an asymptote if there is a value where it's 0. So you want to double check that. Here, this is simplified. There's nothing I can cancel. And if I look at x squared plus 1 equals 0, I'd never actually have to worry about that. This is always at least 0, right? It's x squared. And if I add 1 to it, this is always at least 1. So there are no issues with the denominator in this case. So there are no vertical asymptotes. And then we also have to check our horizontal asymptote. And again, if you need to, you can kind of go back to that little cheat sheet here. Notice that my higher power up top is a 4, and then my denominator has a power of 2. So my numerator has a higher power than my denominator. And when that happens, you have no horizontal asymptotes. So for this case, I have no vertical and no horizontal asymptotes. I clearly know nothing about my graph. I only have 1 point, so I need to plug in a lot more points here. And I'll just give you a couple. So I'm just kind of saving some time for our video where, I know you guys can plug in values, so you can try these at home. Definitely want to pick values on both sides. When you plug in -2, right? So I'll just do one of them. You have -2 to the 4th power over -2 squared plus 1. So the negatives will cancel, and then 2 to the 4th power is 2 times 2, which is 4, times 2, which is 8, times 2 again, which is 16. 2 squared is 4, and then I have 16 over 5. So you end up with 16 over 5 for -2, and you also end up with it for +2. When you plug in -1, you end up with 1/2, and then same thing for +1. Now 16 over 5, well, 5 goes into 16 3 times, and there's 1 left over. So it's a little bit more than 3. You can also use a calculator there with a decimal if you prefer. All right, so let's see, let's graph these. So at 1, I'm at 1/2, and at -1, I'm at 1/2. At 2, 1, 2, I'm a little over 3, so 1, 2, 3, and here 1, 2, 3. Okay. Now I can find a few more points if I want to, but I do know I also have symmetry as well, so it's going to be the same on both sides. And you end up with a U-shaped graph here. Now, hopefully this kind of makes sense if you think about it for a second. So forget about this plus one. If my equation was x to the fourth over x squared, well, you would simplify that. You'd cancel out the two squares, the two x's, and then you'd be left with just an x squared problem, and that's a u. That's a u shape. So that's kind of what's going on here. Because we're only adding that one to it, we're not really changing the base equations too much here. So that's why you are seeing that basic u shape in this case. I do recommend checking with Desmos as well. As we get into higher mathematics and things or more complicated problems, we do rely on technology. So I will be honest about that. You know, really hard polynomials or other graphs, we are using technology to help us find values, to help us learn about them, to help us graph them as well. But it's still good to know some of the algebra, like finding those key points, checking for symmetry, particularly finding those asymptotes. So sometimes just visually seeing a graph is wonderful, but we may not be able to get those little nitty-gritty details. You know, for instance, with an asymptote, maybe you think the value is 1, but actually if I solve for it, maybe it was 1 1/4, right? So you need to still know the algebra to be able to kind of figure out exactly where these key points and these key trends are. But Desmos is going to be really good for any graphing utility to just help you see the overall shape of the graph.